All right. Thank you, everyone, for attending. Special thanks to my committee for the feedback and the assistance, and a special thanks to my advisor for all of the guidance and mentoring through this process. So the title of my dissertation is Analysis of Non-Local Equations, One-Sided Weighted Fractional Sobolev Spaces, and Hamack Inequality for Fractional Powers of Non-Divergence Form Equations. All right. So the structure of the dissertation, as well as the structure of this presentation, is the following. There are 3 chapters. In chapter 1 is the introduction, so that's where we will provide motivation and examples and kind of discuss the types of problems that we're interested in studying. In chapter 2, we will talk about our results for one-sided weighted fractional Sobolev spaces. This project is about fractional derivatives in one-sided Sobolev spaces and uses a lot of techniques from harmonic analysis as well as functional analysis. And in chapter 3, we will prove Hamack inequality for fractional powers of non-divergence form elliptic equations. So this project is a project in PDEs. The research products of this dissertation are these 2 papers. So the first one was published this year in nonlinear analysis, and that's the work from chapter 2. The work from chapter 3 is currently a preprint, but will be submitted soon. All right, so fractional derivatives were first introduced purely as a mathematical concept. Notable names that of people who have defined derivatives of fractional order include Riemann, Liouville, Riesz, Lacroix, and many others. Okay. One example of a fractional derivative is the Marchand left fractional derivative of order alpha between 0 and 1, which is given by this pointwise formula. A couple of things I'd like to point out about this definition is that it is both non-local and one-sided. So to compute the left fractional derivative of u at t, I need to know the values of u from negative infinity to t from this integral. And so we need to know the entire history, the entire past of the function u, and we need to know more than just an infinitesimal neighborhood. That's the idea of being non-local. The reason that I find this particular definition so appealing is because for Schwartz class functions, the Marchand left fractional derivative satisfies this Fourier transform property, that the Fourier transform of the fractional derivative corresponds to multiplication by IC to the alpha. And so here you can see it satisfies these desirable properties, that when alpha goes to zero, you recover the function u, because you just have the Fourier transform of u. As alpha goes to 1, this is the Fourier transform of the derivative, so you recover the derivative, which gives the appeal of why we call it a fractional derivative. So there are a lot of examples where we use these in applications, and one of them is in material science. So if we consider a continuous material where with an external body force being applied, so consider maybe pressing a material down, usually what we measure in experiments is the deformation, which is referred to as strain. When we want to model these materials, though, what's incorporated into the model is stress, which are the internal forces of the material, the particles kind of holding it together and how they act on each other. So to go between what's observed experimentally and a mathematical model, we need to have relationships between stress and strain. So for different materials, there are different relations. So for example, an elastic material, such as a perfect spring, stress is proportional to strain. And so this follows exactly from Hooke's law. For a viscous material, such as honey or water, stress is proportional to the negative velocity of strain. And this is Newton's law. Now, there are other materials, such as viscoelastic materials, that exhibit behaviors of both viscous and elastic materials. So an example is a rubber band. We've all experienced that when you have a rubber band, you stretch it for a long time, it doesn't necessarily go back to its original position. So it has this elastic behavior, but it's not purely elastic. It has these relaxing forces. And it's been observed by engineers that for certain viscoelastic materials, stress is proportional to the fractional time derivative of strain. Okay. So after an internship at Oak Ridge National Lab, my mentor at the lab, Pablo Salazar, my advisor and myself have developed a paradynamic model using fractional derivatives to describe viscoelastic materials with growing cracks. And we want to do analysis on this model, and some of the theory that we develop in this dissertation will be used to analyze these models in the future. But this project is beyond the scope of this dissertation, so I'm not going to talk about that any further. Well, fractional time derivatives tend to be thought of as non-local in time. Fractional powers of second-order differential operators can be regarded as non-local in space. For example, the fractional Laplacian on Rn is given by this pointwise formula. And so you can see again that it's non-local to calculate the fractional Laplacian at a point x in Rn. We integrate over the entirety of Rn. Here we have this limit. This is a principal value integral, and that just has to do with the absolute convergence of the integral. Now, here, unlike fractional derivatives, this is not one-sided. We need to know the values of u in every direction to be able to compute this. This, for Schwartz class functions, this formula satisfies the Fourier transform property that the Fourier transform of the fractional Laplacian corresponds to absolute value of c to the 2s. And so again, here, if I take s going to 1, this is exactly the Fourier transform of the usual Laplacian, which gives the name fractional Laplacian. And as s goes to 0, we again recover the Fourier transform of u. There are many other non-local equations of fractional order that have received a lot of attention in recent years, and this is mainly due to the work of Luis Caffarelli and collaborators. So if you actually go into Google Scholar and you search the exact phrase, or you search for the phrase fractional Laplacian in the title of an article, there are about 1,000 results, 1,000 research papers. But since 2005, there are 900 results. So 90% of the results have occurred since 2005. And in 2005 is when Luis Caffarelli's student Luis Silvestre came out with his dissertation on the fractional Laplacian. Another example of a fractional power of a another example, other than the fractional Laplacian, are fractional powers of nondivergence form operators, which we will be studying in this dissertation. So first, I'm going to talk about the usual Monge-Ampere equation. So the classical Monge-Ampere equation for a convex function u is the determinant of the Hessian of u equals f. So if you recall, the Hessian of u is the matrix of second derivatives of u. So the Monge-Ampere equation is a fully nonlinear equation, because if you recall, the determinant is not a linear operator. So this is nonlinear. For a convex C2 function u, you can check that the Monge-Ampere operator is equivalent to the infimum of, this is essentially affine transformations of the Laplace operator. And this is taken over all matrices B, which are symmetric, positive definite, and have determinant 1. And so what's important here are a couple things, but first, the infimum, so this nonlinear operator is equal to the infimum of linear equations. And this infimum is attained. The other, Caffarelli and Charo define a fractional Monge-Ampere operator by replacing the Laplacian with the fractional Laplacian. And I will just mention that these are degenerate equations because in this class of matrices B, in 2 dimension includes the matrix with epsilon and 1 over epsilon in the diagonal. And as epsilon goes to 0, that degenerates. So we have no control a priori on the eigenvalues. But in the case when the minimum eigenvalue is bounded below, and this infimum is attained, one can show that this equals this fractional power of a non-divergence form operator. And it's because at each point x, the infimum is going to be attained in a different matrix B. So it corresponds to something of this form, where here these coefficients are just bounded measurable functions. Another place we see these operators are in the theory of diffusion processes. So if we consider a particle moving in a heterogeneous domain that is killed when it leaves the boundary, so it is terminated there, this process is generated by a non-divergence form operator with Dirichlet boundary conditions. If you subordinate that process, so you have a jumping particle instead, then this process is, you take the previous process and you subordinate it with an S stable, symmetric, stable Levy subordinator, and that process is generated by fractional powers of this non-divergence form operator. So we will be studying regularity estimates for equations with operators. Okay. So now I'd like to describe the objectives of the rest of the dissertation. So first, we want to define and characterize appropriate one-sided weighted Sobolev spaces for fractional derivatives. The first question here is, how do we define one-sided distributional spaces that take into the behavior of these one-sided objects? And we'll see very momentarily that this is a non-trivial question. We'd also like to define one-sided Sobolev spaces, and this is where we use the weights, and we have weighted Sobolev spaces. And we are also interested in the limits as alpha goes to 1 and 0 of these fractional derivatives in the weighted LP norm and almost everywhere, which again is entirely a non-trivial argument. Second, we will prove Hamack inequality for fractional powers of non-divergence form elliptic equations. The first thing we encounter is how to define fractional powers, how to define these fractional operators, because these non-divergence form equations, there's no natural Hilbert space structure, so there's no Fourier transform. So how do we define this? The second thing we need to overcome to prove Hamack inequality, is the non-locality of fractional operators. So we use a degenerate local PDE to characterize these equations and prove Hamack. Now, with this characterization, now we need to overcome the degeneracy of it. And within that, we will see that there's an underlying Monge-Ampere quasi-metric space that we need to work in, which brings additional challenges. Oops. And third, we're seeking a fully non-divergence form proof. We don't want to use any divergence techniques. So we'd go to go full non-divergence. Okay. So without further ado, let's discuss chapter 2. One-sided weighted fractional Sobolev spaces. Okay. So let's take a function phi that's smooth with compact support. And we're going to define the left and right derivatives. These are classical derivatives in terms of the one-sided limits of the difference quotient. And so if we integrate the left derivative of u against a test function, you can show pretty easily that this is equal to negative u integrating against the right-sided derivative of phi. Well, phi is a smooth function with compact support. So this is exactly the derivative. And what is this? This is the distributional derivative of u. And so left derivatives are exactly the usual derivatives in the sense of distributions. So when we start talking about these one-sided classical derivatives, the one-sidedness is lost as soon as we go into this weak setting. So we would like to define or develop a distributional setting where we can incorporate this one-sided property that we see in fractional derivatives. So if you recall, the Marchand left fractional derivative of order alpha is given by this formula. Similarly, the right fractional derivative is given by where we integrate from t up to positive infinity. So it looks at the future with a similar formula here. Now, if you take two Schwarzkopf functions, u and phi, you can show that the left fractional derivative integrating against phi equals u integrating against the right fractional derivative of phi. And so we are going to define our class of test functions to be the set of Schwarzkopf functions that are supported on the left. So there exists some real valued number a such that the support of phi is contained from negative infinity to a. And now if we look up at our this expression here, the reason we do this is because if phi is supported on the left here, then I'm only looking at the left fractional derivative of u on the left. I don't need to know what happens in the future to be able to compute this. And similarly, if I look, if you look at the pointwise formula for the right fractional derivative, then this will also be supported on the right. So on this side of the equation, I'm only looking at the values of u. I'm sorry, this will be supported on the left. So I'm only looking at the values of u on the left again. It's exactly what this says. Moreover, the right fractional derivatives satisfy this decay. And so if u is a locally integrable function with respect to this decay from negative infinity to a for all a, then the left fractional derivative is well defined in the sense of distribution, and the way it behaves is it acts on a test function by u integrating against the right fractional derivative. And so this gives us this one-sided distributional setting for our fractional derivatives. So next, we want to talk about our one-sided Sobolev spaces. So to do that, we are going to use weights and do weighted Sobolev spaces. So first, if you recall the Hardy-Littlewood maximal function, the one-sided Hardy-Littlewood maximal function for the left one is given by the left-sided, you take all the left-sided averages of u and you take the supremum over all those averages. And the weights we choose are the good weights for this operator. So if you take our weights omega will always be positive, locally integrable. When p is between 1 and infinity, we say omega is in this class AP minus the Sawyer class of weights if this integral condition is satisfied. And what Sawyer proved was that omega is in this class if and only if the left Hardy-Littlewood maximum function is bounded from weighted LP into weighted LP. And that's the property that we utilize. In the case of p equals 1, we say omega is in a1 minus if it satisfies this condition here where the m plus, you take the supremum of all right-sided averages. And Martin Reyes and company showed that this is bound, these weights are such that, excuse me, the M minus is bounded from weighted L1 into weak weighted L1. So you can see from the operator as well as these conditions that these weights are indeed one-sided. So for one of our weights, omega in AP minus, and maybe I'll go back briefly and just say that these are a very general class of weights. They include the classical Monge-Ampere weights. They also include any decreasing function. So for example, e to the negative t is in the class of Sawyer weights. So a very general class of weights. So we take one of these weights and we define our one-sided weighted Sobolev spaces to be the functions u in weighted LP such that their derivative is also in weighted LP with the norm that you would expect. And so we see that these are one-sided and that they're good for working with fractional derivatives, as we'll see from the next slide. So the first result of this chapter is our characterization. So if we take a function u in our weighted LP space for one of our Sawyer weights, and we additionally assume that u has a derivative in weighted LP, so it's in our Sobolev space, then the left fractional derivative, which a priori is just a distribution, is actually a function in weighted LP. The function agrees with the Marchand pointwise formula almost everywhere, and it satisfies this interpolation estimate. Moreover, we have the limiting properties that we desired, that when I take the limit as alpha goes to 1 of the fractional derivative, I recover the derivative where that limit can be taken in weighted LP as well as almost everywhere. And the limit as alpha goes to 0 of the fractional derivative goes to u, where again that limit can be taken in weighted LP and almost everywhere. The converse of this theorem is we again assume that u is in weighted LP, and this time we assume additionally that the left fractional derivative is in weighted LP and that it converges in the LP norm, weighted LP norm, as alpha goes to 1. And then we are able to show that u has a derivative in weighted LP and that it converges to exactly what we want it to. It converges to the derivative, where again that limit's in weighted LP and almost everywhere. Similarly, if we this time assume that it converges as alpha goes to 0, then it converges to exactly what we expect. It converges to the function u, where we can take that limit in weighted LP as well as almost everywhere. So a key to proving almost everywhere convergence is we need maximal estimates. So the estimate that we prove is that if we take a function or a weight, omega, in our class of Sawyer weights, and we take u to be in our weighted Sobolev space, then this pointwise formula, which a priori is just a formula, is bounded independent of alpha by a constant, a universal constant, times the maximal function of the derivative plus the maximal function of u. So here this constant is independent of u, p, alpha, t, everything. And this has a couple really important consequences. So the first one is that when p is between 1 and infinity, by the boundedness of the maximal operator, this formula immediately is a function in weighted LP. And by a distributional argument, we show that this formula coincides with the left fractional derivative. So now we know that this here is the left fractional derivative, and we're taking the supremum over all orders of the fractional, or all orders of the fractional derivative. So this is a maximal function here, and this is a maximal estimate that we use to prove the almost everywhere convergence as alpha goes to 1 and 0. Okay. So now we'll talk about the material from chapter 3. So we're going to prove Hamack inequality for fractional powers of nondivergence form elliptic equations. Okay. So we're interested in non-negative solutions to this fractional Poisson problem, in where we have fractional powers of the non-divergence form operator of u equals f in a bounded domain omega with u equals 0 on the boundary. S will always be between 0 and 1. We will assume the aij's are uniformly elliptic, meaning that there exists little lambda and capital lambda such that this condition holds. We also assume they're symmetric. And for reasons that we will see momentarily, we will also additionally assume that they are Hölder continuous, and that the left-hand side, or the right-hand side, f is bounded in omega. So the first difficulty that we encounter, the first question we should ask, is how to define fractional powers of non-divergence form operators. As I mentioned previously, there's no natural Hilbert space structure here, no Fourier transform. So how do we define this? The motivation, one of the motivators, is this formula here. So for any lambda bigger than 0 and s between 0 and 1, you can write lambda to the s in terms of this integral that comes from the gamma function. So here I have 1 over gamma minus s. Now, using the definition of Balakrishna for fractional powers of operators, you can think about replacing this lambda with an operator, where here inside this is like the identity. So you have u, and then you have this object here. Well, what is this? This is the heat semigroup acting on u. So it's a solution to the heat equation generated by L with initial data u. And in the case of the fractional Laplacian, if you take L to be the Laplacian, then this formula is fully justified using the Fourier transform. In our setting, if we take our coefficients aij to be Hölder continuous, our operator L to be our non-divergence form operator, and our domain to be the set of C2 functions that are continuous up to the boundary and 0 on the boundary, such that L of u is continuous and 0 on the boundary, then Arendt and Schatzel showed that L generates a C0 semigroup, which means that we're able to solve a heat equation, and this formula is well defined. And so that's why we have the assumption that our coefficients are Hölder continuous, so that we have a well-defined definition of the fractional operator. Okay. Now we state our the next main result. So we suppose that our coefficients are Hölder continuous, and then we show that there exists positive universal constants. So here, when I say universal, I mean that they only depend on dimension, the ellipticity constants, and the power s. So there exists constants c, gamma, and k, such that for every ball, such that when I enlarge the ball by k, it's compactly contained in omega. And for every non-negative solution, u, that's C2 in the ball, to this fractional, to our fractional equation, then we have that the supremum in a smaller ball, so here gamma is less than 1, the supremum in the smaller ball is controlled, this is a universal number, by the infimum in that smaller ball plus the L infinity norm of f. And so this, you're controlling the supremum by the infimum, so this tells you how much the solution can grow. It's controls the oscillation of the function. And an immediate consequence is interior Hölder regularity from the proof of Harnack inequality. Okay, so to prove this, one of the things we have to overcome is the non-locality of this fractional operator. So we use an extension characterization by Galemayana and Stinga from 2013. And this is a more general case than the extension problem that was made popular in the in the PDE setting by Caffarelli and Silvestre for the fractional Laplacian. And so if we take a function, so we define this PDE here in dimension Rn plus 1. So we're increasing the dimension, and the idea, so I'm going to be showing a couple pictures just with my screen during the rest of the talk, so, or for part of it. So the idea is, okay, you take your domain omega and you increase it, you extend it by one dimension using the variable z for z bigger than 0. And we prescribe our normal data, our derivative with respect to z, at z equals 0 to be this function f. And then up to a multiplicative constant that only depends on s, we take the solution, capital U, we take the trace at z equals 0, that is little u of x, where little u solves our fractional Poisson problem. So by solving this equation here in capital U, we can solve, we can study, or by studying this the solution for capital U up here, we can study the behavior of the solution little u to our fractional equation by taking the trace. So I'll just note a couple of things up here is that you'll see this is our non-divergence form operator, the non-fractional power, and we have the z to the 2 minus 1 over s. And so this is a degenerate equation because depending on if s is 1/2, then this is just 1. But if s is less than 1/2 or bigger than 1/2, then this either goes up to infinity or down to 0 as z goes to 0. So it is degenerate in that sense. So now I want to demonstrate how proving if we have Hamack for the extension equation, so I would just refer to it as capital U, then we have Hamack inequality for little u. Okay, so the first thing we will do is we want to talk about what happens across z equals 0. So we will do an even reflection across z equals 0. So if we have our solution for z bigger than 0, this part here, then we define the even reflection by just reflecting. Is that better? Okay, by just reflecting across z equals 0 in this way. So now we can study what happens across z equals 0. And so the equation that we now consider is where the only thing that changes is this absolute value of z from the even reflection, and z is any positive or negative. So suppose we have Hamack inequality for capital U in a ball BR cross -1, 1. So the BR is an x, the -1, 1 is an interval in the variable z. So Hamack inequality says that the supremum in that set is controlled by universal constant, the infimum of U, plus the L infinity norm of the right-hand side, which in this case is still f. Now, by taking the trace, capital U, and we look at across z equals 0, well, capital U, is little u, and since the set BR in X is smaller than BR cross -1, 1, the supremum is indeed smaller, which gives us this inequality. On the other side, similarly, by taking a smaller set BR, the infimum is larger. So we have that the infimum of capital U across this set is smaller than the infimum of little u. So from here on out, we will focus on proving Hamack inequality for capital U. And I will just mention that our proof for proving Hamack inequality for capital U, we only use that the coefficients are bounded measurable functions. So the Hellwig continuity is not essential for this argument. That's what we use to define our fractional operator and justify the characterization. Okay, so within our extension equation, there's an underlying Monge-Ampere geometry. So I'd like to recall the Monge-Ampere equation we saw at the beginning of my talk, which again is given by the determinant of the Hessian of P equals F. So different notation, same equation. And as I said before, this is a fully nonlinear equation. So one thing you can do to study regularity estimates of this is take the directional derivative in the direction of E, and then this becomes a trace equation. So on the right-hand side, I just have the directional derivative of F. I have the trace, and then here I've got a matrix that has to do with the function phi, and then I've got the Hessian of the derivative in the direction of E of phi. So if I relabel this equation, then this is the trace. I have a matrix, the Hessian of U equals F, just by relabeling. And so this is a linear equation, and it's called the linearized Monge-Ampere equation. So Caffarelli and Gutierrez, under certain assumptions on the function phi here, proved Hamack inequality for the linearized Monge-Ampere equation, but they didn't do it in Euclidean balls. They did it in Monge-Ampere sections. And so the sections are what makes sense for the geometry of this equation. So to kind of demonstrate that, first, if you consider a supporting hyperplane to the function phi at a point x naught, then the Monge-Ampere sections are described as follows. Okay, so this is our convex function phi, and you take a supporting hyperplane at the point L naught, and then you lift it up by adding plus r. And the Monge-Ampere sections are the points where this hyperplane L naught plus r are above our convex function phi. So they're given by this here. And so those are they're the sublevel sets of phi minus the hyperplane L naught. And so those are the Monge-Ampere sections as we see here. And if you bring the L naught to the other side, and we know how to write down what a supporting hyperplane is, we have this expression, and that is exactly the Monge-Ampere quasi-distance associated to phi. So the distance between a point x naught and x is phi of x minus the supporting hyperplane. And this is indeed a quasi-distance, meaning that it satisfies the triangle inequality, but with a constant in front, where that constant is bigger than or equal to 1. As well as the other thing is that this is not symmetric, which causes brings additional challenges when you work with this. And the other piece is the Monge-Ampere measure associated to phi. So the measure of a Borel set E is the Lebesgue measure of the gradient of phi of that set E, which for a sufficient function phi is given by the integral of E, the determinant of the Hessian of phi. And so this geometry gives us a quasi metric space to work in. And so we will prove Hamack inequality in Monge-Ampere sections. And for our setting, for our equation, we define a function capital phi from Rn plus 1 to R for our extension equation in x and z by x squared in x plus z to the 1 over s in z. Then you take z, s equals 1/2, then this is z squared. And if you look at the linearized Monge-Ampere equation, for this function phi, the Hessian of phi that's given by this, what we see on the left-hand side. So we take the inverse of the Hessian of phi, which in x is just the identity, and in z, you take second derivatives, you have 1 over s minus 2. So in the inverse, you have 2 minus 1 over s. And now you compute, you multiply these matrices and take the trace, and you have the Laplacian in x, and the degenerate term z to the 2 minus 1 over s. And because our coefficients aij are uniformly elliptic, they're comparable to the identity, and so our extension equation is comparable to this linearized Monge-Ampere equation. And so we will use the underlying geometry, the Monge-Ampere geometry for this function phi, and prove Hamack inequality in those sections. So we define paraboloids with respect to this geometry to be the paraboloids with opening A and vertex xv zv by negative a times the distance from the vertex to a point x plus a constant c. So in the case when s equals 1/2, this is like the vertex minus xz squared. So again, these are our paraboloids, and I'm defining them because that's what kind of the basis of our proof for Hamack inequality. So we will apply, so now I'm going to just describe our strategy behind Hamack inequality. So we apply the method of sliding paraboloids that Ovidio Savin used in 2007 for uniformly elliptic equations. And the idea is we take these paraboloids that I defined on the previous slide, fixed opening, and you slide them up from below until they touch the graph of u for our function u for the first time. And wherever it touches, we call those contact points. And we're going to measure those contact points, and the measure being the Monge-Ampere measure. So by increasing, and the idea is we increase the opening of these paraboloids, meaning that they become narrower. And as I lift narrower paraboloids from below, I can touch up more and more points the function, and we show that the set of contact points almost covers and measure the domain. And so now, if we can control, and they're touching from below, so if we can control the height of these paraboloids, we in turn control how high the function u can go. So it's controlling, again, the height of the function. The first thing we do here is we don't want our contact points to happen on the set z equals 0, because at z equals 0, we have the Neumann condition. So what we do is we add this barrier, which is negative a constant, absolute value z, plus d. And okay, what this does is it lowers the function down. See this part here, it lowers it down around z equals 0, and we show that you cannot touch along z at z equals 0 by a z1 function from below. And in fact, you touch at a positive distance away. So then all of our contact points have to happen away from z equals 0, not on the boundary. So then the first thing we show, our first lemma, is that the measure of the contact points is a universal proportion of the measure of the vertices. So this is comparable to the usual ABP estimate. The second thing we show is that if we can touch u from below with a paraboloid of opening A in a Monge-Ampere intersection SR, then in a smaller section as A to R, we can touch from below with paraboloids of greater opening, which means narrower paraboloids. And these make up a universal portion of the original set SR that we touched in. So the idea or the takeaway from this lemma is if you can touch at a point in SR, then nearby you can touch with narrower paraboloids. And you can touch with narrower paraboloids, yes. And the third lemma is a covering argument, Calderon-Zygmunt type covering argument, because we want to take this lemma 2 and talk about it across, we want to be able to move it around the entire domain to be able to do this argument that you touch at a point nearby, you can touch with a narrow parabola, and then nearby a narrower parabola, and so on and so on and so on, and increase the openings, and therefore, we increase the height of them as well. So I will mention that the proof of these lemmas, as well as of Harnack inequality, are very technical. So I'm not going to go through all of them. I'll just mention for lemma 2, this uses a very, very delicate barrier argument to localize in the section S A to R. And for lemma 3, we use a Vitali covering lemma that only works in our case because we have separated variables, because x and z are indeed separated in this function phi. Excuse me. So I will briefly provide a sketch of the proof of lemma 1, where the measure of the contact points controls the measure of the vertices. Okay. So for convenience, let's let B be the measure, the set of vertices, and A be the set of contact points. And let's take a paraboloid P of opening A that touches U from below at a point x naught, z naught. And in that case, I have an explicit expression for my paraboloid P. Because P touches U from below at x naught, z naught, and it's an interior point, excuse me, it attains a minimum at the touching point, which means that the derivative is 0 at that touching point. So we have this equality here, and I know exactly what P is, so I can take the derivative, and it's the derivative of phi at the touching point minus the derivative of phi at the vertex. And this gives us a description of the vertices. So we can solve this here for the derivative of the vertex. You divide by A and move that to the other side, and you get this equality here. And so this is how the vertices are uniquely determined in terms of the contact points. And so we define a map T from the set of contact points to the derivative of phi, this set here, the derivative of phi of the vertices, in this way. And because we don't touch on the set z equals 0, and we are, in fact, a positive distance away, this is a Lipschitz map on the set of contact points. The only problem with phi is at z equals 0. And the other piece, before we demonstrate the estimate, is we have control of the Hessian of u at these contact points. So the lower inequality, and that control is in terms of the Hessian of phi. So this first inequality here just comes from the fact that P touches U from below at x naught, z naught, and the Hessian of P is the Hessian of phi, explicitly with this negative A in front. On the other end, it's controlled by a universal constant CA, Hessian of phi again. And this inequality comes from the fact that U solves an equation. So with these, we sketch the lemma. So the measure, so we're trying to, excuse me, so the Monge-Ampere measure of a set of vertices, by definition, is the Lebesgue measure of the derivative of phi of the vertices. And this equals, by our map T, the integral over T acting on the set A. And we'll call T is a Lipschitz map on A, so we use the Lipschitz formula for, we do change of variables for Lipschitz maps. and we integrate over A and the determinant of dt. And we know exactly what t is, so it's the derivative of this thing here, so we have the second derivative. And now, from our last estimate on the previous slide, I know that the Hessian of u is controlled by that universal constant, which is the Hessian of p. And here I have the 1 over a, so the a cancels, and I just have c plus 1, Hessian of phi. I can pull that outside, and I'm just left with this term here, and this is exactly the Monge-Ampere measure of the set A. So now this is a large universal constant. You bring that to the other side, it becomes a small universal constant. So I have that the measure of the context points make up a universal proportion of the measure of the vertices. And with that, I will end.